Hello everyone! Today I will be talking about modeling highway fuel economy using regression. This project explores how vehicle design features influence fuel efficiency using statistical modeling. The goal of this analysis was to build a statistical model that explains which vehicle characteristics influence fuel efficiency, specifically highway MPG. To do this, I began with an initial manual model, then used forward stepwise model selection to explore and compare multiple models. Finally, I interpreted the results and connected fuel economy to sustainability. So let's get into it. For this project, I used the 2025 Fuel Economy Dataset from the U.S. Department of Energy. This data is collected through standardized vehicle testing conducted by the Environmental Protection Agency, along with manufacturer-reported data that is verified by the EPA. Testing takes place at the National Vehicle and Fuel Emissions Laboratory in Ann Arbor, Michigan. For my analysis, I focused specifically on highway fuel economy because highway driving tends to be more consistent and less affected by stop-and-go conditions compared to city driving. To guide my variable selection, I consulted with my dad, who is a master mechanic. Together, we identified variables that are mechanically meaningful and likely to influence fuel efficiency. These included the number of cylinders, fuel type, which includes premium, regular, premium required, diesel, and mid-grade gasoline, as well as drive system, which included all-wheel drive, front-wheel drive, rear-wheel drive, four-wheel drive, and part-time four-wheel drive. I also excluded variables like vehicle make and model because including them would lead to overfitting. The make and model variables essentially encode for MPG directly, which would reduce the interpretability of the regression model. After reviewing all of the variables in the dataset, the one that stood out as most likely to influence fuel economy was engine displacement. Engine displacement refers to the volume of air that the engine consumes or pumps through, and larger displacement engines require more fuel to generate power, which typically leads to lower fuel efficiency. Because of this strong expected relationship, I chose to exclude engine displacement from my initial modeling process and treat it as a holdout variable. This allowed me to later test whether engine displacement adds statistically significant explanatory power to the model after accounting for other variables. It's also important to note that engine displacement is correlated with the number of cylinders, which introduces the possibility of multicollinearity. Because of this, I will be able to test whether engine displacement adds any new information that cylinders already haven't explained. I think this is an interesting variable to exclude initially and evaluate later in the analysis. To begin the modeling process, I built a linear regression model. The response variable is highway fuel economy, and the predictors include the number of cylinders, drive system, and fuel type. The model explained about 56% of the variation in fuel economy based on the adjusted R-squared value. The overall model was highly significant with an f-test p-value smaller than 2.2 times 10 to the negative 16th. Looking at the coefficients, the number of cylinders had a strong negative effect on fuel economy. Each additional cylinder was associated with about 1.8 mile per gallon decrease in highway MPG. Drive system also had a significant impact on fuel efficiency, which makes sense mechanically since systems that power more wheels require additional energy. However, the diagnostic plots revealed some issues with the model assumptions. The residuals versus fitted plot showed a cone-shaped pattern suggesting non-constant variance, and the Shapiro test and the QQ plot indicated that the residuals were not normally distributed. Because these assumptions were not fully satisfied, the next step was to explore a log transformation to see if the model could be improved. So to see if I could improve the model, I explored a log transformation of the response variable highway fuel economy. The table shows a comparison between the model built with the raw response variable and the model using the log transformed response variable. The log model explains more variation in the data with an adjusted R-squared value of approximately 0.616 compared to 0.562 for the raw model. Additionally, the residuals versus fitted plot for the log model showed that it improved constant variance compared to the cone-shaped pattern observed in the raw model. The Shapiro test also showed improvement in the distribution of the residuals. While the residuals are still not perfectly normal, in the log model with a p-value equal to 4.38 times 10 to the negative 8th, the distribution is closer to normal compared to the raw model, which had a p-value less than 2.2 times 10 to the negative 16th. Fuel efficiency relationships are often multiplicative rather than linear, and the vehicle design changes often affect fuel efficiency by percentages rather than a fixed MPG. Because the log transformation helps capture these relationships and improves the model assumptions, the log transformed model was selected for further model development. In this log model, the response variable is the natural log of the highway fuel economy. Because of this transformation, the coefficients represent approximate percent changes in MPG. For example, the cylinder coefficient of negative 0.072 indicates that each additional cylinder decreases highway fuel economy by about 7.2% when the other variables remain constant. Similarly, vehicles with all-wheel drive have about 14% lower highway fuel economy compared to the baseline category of front-wheel drive vehicles. Rear-wheel drive vehicles also have a 17% lower MPG, and four-wheel drive vehicles show the largest decrease with roughly 32% lower MPG. Two fuel types showed statistically significant effects in the model. Diesel vehicles had a positive coefficient of approximately 0.104, which corresponds to about a 10% increase in highway fuel economy compared to the baseline category of regular gasoline vehicles. Vehicles that require premium gasoline had roughly a 5% decrease in highway fuel economy relative to the regular gasoline vehicles. The other fuel types, mid-grade and premium, were not statistically significant, but further analysis needs to be done to find the best model. To continue the journey, I explored whether additional vehicle characteristics could improve the model by using stepwise model selection. In this step, I introduced additional predictors including transmission type, the number of gears, and whether the vehicle included stop-start technology. I used BIC with a forward stepwise selection, which begins with a simple model and progressively adds predictors. BIC helps balance model fit and model complexity by penalizing models that include too many variables, and this helps prevent overfitting. According to the BIC results, the best model included 11 predictors. However, the difference between the 10 and 11 predictor models was very small when examining the selection criteria plot. Further inspection showed that one of the predictors in the 11 predictor model was not significant. Removing that variable did not meaningfully change the model fit, so the simpler 10 predictor model was selected. This decision follows the principle of parsimony, which states that when two models explain the data equally well, the simpler model should be preferred. So in addition to the variables from the original model, the stepwise model identified selectable continuously variable transmissions and manual transmissions, as well as the number of gears as additional predictors that help explain variation in highway fuel economy. These results are reasonable because transmission design and gear ratios directly affect how efficiently engine power is converted into vehicle motion. This model also removed premium, required, and mid-grade gasoline as significant predictors of fuel economy. I think it's important to note that the start-stop technology was dropped from this final model. Since our analysis focuses specifically on highway fuel economy, where the engine is running continuously, the data confirms that the start-stop systems do not offer fuel economy savings on the highway, but this could be a significant during city driving where the engine can shut off at intersections. To evaluate whether adding predictors improved the model, we compared the log manual model with the stepwise model. The stepwise model increased the adjusted R-squared from about 0.62 to 0.68 and reduced the residual standard error. An ANOVA comparison confirms that additional predictors significantly improve the model fit with a p-value less than 2.2 times 10 to the negative 16th. Therefore, the expanded stepwise model was selected as our final model. Next, I evaluated whether interaction terms between variables could improve the model. Specifically, I tested interactions between cylinders and drive system, as well as cylinder and transmission type. The motivation for these interactions is that the effect of engine size might depend on the type of drivetrain or transmission. For example, the impact of increasing cylinders could differ between all-wheel drive and front-wheel drive vehicles. However, after fitting these models, most interaction terms were not statistically significant. Only a few showed weak significance, and overall, the inclusion of interaction terms did not meaningfully improve model performance. The adjusted R-squared remained nearly unchanged, and the residual standard error showed no statistical improvement. Because the interactions did not provide a meaningful gain in explanatory power and made the model more complex, they were excluded from the final model, and this decision supports maintaining a simpler, more interpretable model. The final model explains about 68% of the variation in highway fuel economy, and all predictors included in the model were statistically significant. Because the response variable was log transformed, coefficients can be interpreted as the approximate percent changes in fuel efficiency. For example, each additional cylinder was associated with about a 6.2% decrease in highway fuel economy when holding the other variables constant. Vehicles with all-wheel drive have about 11% lower highway fuel efficiency compared to front-wheel drive vehicles. Vehicles with part-time four-wheel drive have about 20% lower highway fuel efficiency. Rear-wheel drive vehicles have about 11% lower highway fuel efficiency, and vehicles with four-wheel drive have about a 23% lower highway fuel efficiency. Diesel vehicles have about a 19% higher fuel efficiency compared to regular gasoline vehicles, and premium gasoline vehicles showed about a 5% higher highway fuel efficiency compared to the regular gas. Manual transmission vehicles have about 11% lower highway fuel efficiency compared to automatic transmissions, and each additional gear was associated with about a 2.9% decrease in highway fuel efficiency, possibly reflecting performance vehicles with more complex drivetrains. Overall, the strongest factors affecting highway fuel economy in this model are engine size, drive system type, and transmission type. Diagnostic plots indicated that the model assumptions are reasonably satisfied. The residuals seem to be approximately normally distributed based on the QQ plot. Although the Shapiro test is still not normal, the p-value is closer to 0.05 than the earlier log model. With a large sample size of over 800 observations, even a very small deviation from perfect normality can make the data not normal. But I believe that normality assumption can be considered reasonably satisfied. Constant variance also seems to be reasonably satisfied based on the residuals versus the fitted plot. Since the dataset consists of individual vehicles, the independent assumption is reasonable. The data is observational, so the results represent associations rather than causal relationships, and can only be applied to the same vehicles from 2025. If you remember back to the beginning, I chose to hold out on adding engine displacement. I did this because I believed that larger engines would have a greater engine displacement and burn more fuel per combustion cycle, so I expected it to influence fuel efficiency. After selecting the final model, I added engine displacement as an additional predictor to test whether it explained any additional variation in highway fuel economy beyond the variables already included in the model. The estimated coefficient for engine displacement is approximately negative 0.036, which corresponds to about a 3.6% decrease in highway MPG for each additional unit of engine displacement, when holding the other variables constant. More importantly, the p-value for engine displacement is 0.000999. This p-value tests the null hypothesis that the Chucro coefficient for engine displacement equals 0, meaning that engine displacement has no relationship with highway fuel economy after accounting for the other variables in the model. Because the p-value is so small, we reject the null hypothesis. This also means there is convincing evidence that engine displacement is related to highway fuel economy in my model. This tells me that engine displacement provides additional statistically significant information for explaining highway fuel economy, even after accounting for factors such as cylinders, drive system, fuel type, transmission, and number of gears. When examining the 95% confidence interval for the exponentiated coefficient, it ranged from 0.944 to 0.985. Because this interval is below 1, it indicates that larger engine displacement is continuously associated with lower highway fuel efficiency. Interpreted in percentage terms, this suggests that each 1 unit increase in engine displacement is associated with roughly a 1.5% to 5.6% decrease in highway MPG when holding the other variables constant. In addition, the adjusted R-squared of the model increases slightly from about 0.78 to 0.862 after adding engine displacement. This indicates that including this variable improves the model's ability to explain variation in the highway fuel economy. This project relates to sustainability because transportation is a major contributor to global carbon emissions. Transport accounts for roughly 1/5 of global carbon dioxide emissions, and about 3/4 of those emissions come from road transportation such as cars, buses, and trucks. Because passenger vehicles make up a large portion of these emissions, improving vehicle fuel efficiency can play an important role in reducing the environmental impact of transportation. This issue is becoming even more important as global demand for transportation continues to grow. As populations increase and incomes rise, more people can afford personal vehicles, and global car ownership is expected to increase significantly in the coming decades. Currently, there are already more than 1 billion vehicles in use worldwide, and the global vehicle population is rapidly moving towards 2 billion. More vehicles generally lead to greater fuel consumption, increased demand, and higher carbon dioxide emissions, which contributes to climate change and other environmental changes. Another important sustainability concern is the finite nature of our global oil reserves. Personal vehicles are heavily dependent on petroleum-based fuels, meaning that continued increase in vehicle use directly translates into an increased oil consumption. As vehicle populations grow, the demand for oil rises accordingly, placing additional pressure on resources that are inherently limited. This creates a long-term sustainability challenge because improvements in efficiency alone may not fully offset the effects of the growing demand. As a result, reducing fuel consumption through more efficient vehicle design and a better understanding of the factors that influence MPG becomes important, not only for lowering emissions, but also for addressing the global depletion of oil reserves. Because these trends in improving fuel efficiency and understanding the factors that influence vehicle MPG are important for reducing energy consumption and emissions. By modeling highway fuel economy and identifying the mechanical factors that influence it, this project helps highlight how vehicle design characteristics can impact fuel use and therefore sustainability. One of the most challenging parts of the modeling process was using stepwise model selection and deciding which predictors to include in the final model. This was a new method and it required testing multiple model combinations and comparing their performance rather than relying on a single fixed approach. Determining which variables improved the model and which did not was not always straightforward, especially because some predictors showed only a small change in model fit. In the end, the goal was to balance model accuracy with simplicity, which led to removing variables that did not provide meaningful improvement while retaining the most important predictors of highway fuel economy. In addition, some predictors were closely related to each other. For example, variables such as the number of cylinders and engine displacement both represent aspects of engine size, which required careful interpretation. Despite these challenges, the final model satisfied the major regression assumptions and provided meaningful insights into the factors that influence highway fuel efficiency. All of this made me curious about how my 20-year-old car compares to the newer model. I mostly do city driving, and my 2005 BMW X5 gets about 19.3 miles per gallon in the city, while the 2025 BMW X5 gets about 23 miles per gallon in the city. This could reflect some improvements in engine efficiency and vehicle technology over time. While the newer BMW X5 has better fuel economy, as I found throughout this case study, the difference is most likely not due to just one factor, but a combination of engineering changes that help make the car more fuel efficient. This assignment helped me understand how vehicle characteristics such as engine size, drivetrains, fuel type, and transmission systems influence fuel efficiency, and how statistical modeling can help connect vehicle design features to real-world fuel efficiency and broader sustainability outcomes. Thank you so much for listening.